Okay, so I'm going to make a video on beating per request. When we have beating, what that means is the natural frequency of the system is approximately equal to the driving frequency of the system. They are not equal, but they are close to being equal. And that causes this interesting phenomena where if you were to go ahead and plot what this looked like as a function of time, you would see typical oscillations like we would with any type of vibrating system, but the amplitude of that system also changes as a function of time. So if I were to, I'm going to try to draw this slowly. So you see at this point, I drew it big, and I'm going to get smaller. Like that. If you were to look at the equation for this, and again, we're not going to worry about deriving this. I'm not going to ask you to derive this on any exam because it's a lot of like funky manipulation. But what you see is that the displacement x of t, which is again this thing on the y-axis, this is to the normalized force, that's big F naught over m, over the differences of the frequencies squared. That's going to be multiplied by sine of omega n plus omega over 2t times sine of omega n minus omega over 2t. And this is our beating phenomenon. Now, if you look, we really, let's see if I can make this a little bit longer. I'm going to copy and paste this curve at least. I'm going to try to. That's good enough. So if you were to look at the two frequencies at play in the system, no, we have these two sine waves multiplied by each other. So that is what is causing the change in amplitude. One of these sine waves is representing the oscillations that are occurring in this picture, like the actual motion of the mass moving back and forth, while the other one is kind of hidden, and that is the behavior of the beat itself. So if we look, let's say, at this guy, this frequency, if we think about omega and being close to each other, and we look at it compared to this guy, the one that I have currently in red is going to be bigger. This is a large frequency. Meaning you have many cycles per second. What that ends up matching is the actual oscillations of the mass. So let's say that, let's say I have this right here. This is 1 second. Actually, let's not move it there. Let's make it so it's actually a line sinusoidal. Let's say it's here. Say this is 1 second. If we were to actually look at this, we can see that we have, that's one graph. That's 1, 2, 3, 4 cycles in this second. So in this example here, this would have a frequency, and I'm going to call this frequency of the oscillation of 4 hertz. I can kind of get that just by looking at the graph that I drew. Again, it's arbitrary, but I drew that. And that's what happens with the oscillation. Another thing you can do is you can look at the period of the graph. So if I were to look at this, not at that graph, sorry, the period of the motion, which would be this, because that graph would be the period of this curve that I just drew in red. That's one period of the motion. Make that clearer. That's one period of the motion. In this example, this would have to be 0.25, which means you have 0.25 seconds per period. After 1 full second, 4 cycles have completed. This would be 0.25 seconds. So that's going to be related to this omega up here. This is the large omega. So if we were to say that omega oscillation is 2 pi times that, this whole thing would be equal to omega n plus omega over 2. And that's based on the oscillations. That's a high frequency, many cycles per second. That's exactly equal to the oscillation of the mass. That's exactly equal to this term here, omega n plus omega over 2. Now, the other frequency is a little bit more confusing. Let me go ahead and, oops, I have to erase all of that. I really just want to erase the red. Okay, that's not bad. So if we look at, let's go ahead and make this blue. If we look at this thing, omega n minus omega over 2, that is representing another sine wave that will actually be the envelope of this. Did that really crappy, but then again, I drew it crappy. That represents the envelope of the motion. So if we wanted to know the frequency of the envelope, that would really be 2 of these beats. And we'll discuss what that means in a second. But if we're looking at this just from the mathematical perspective of sine of some omega times t, that omega is representing this sine wave that I just drew in blue. Because again, this would be a low frequency, smaller number of cycles per second. But they don't define the beat frequency as being equal to the envelope of the sine wave. The reason why is that if you think this in terms of volume, because we showed that video in class where the professor had these 2 tuning forks that are at slightly different frequencies, and you hear the volume when he hits them go from low to high, and then it repeats. It'd be low, low, you know, it's going to go from low to high. I'm sure that'll be a meme. So if you were to think about the beat, one beat, that beat starts over right here. Again, let's look. We're low, oops, we're low, we're high, we decrease back to low, and then we start again. You remember, I copy and pasted this thing at the beginning. That's going to be the one period of the beat. That's one full beat before it begins. So really what we see is that it's common to define the beat frequency as being this until that point. Now, if you compare that to what you have up here, when we divided by 2, that made the number of cycles per second smaller. We halved it. So if this is the beat, one of these things, and if you compare it to the original one, which looked like this is really going to have a frequency that is twice that, because of the fact that we are looking for something that is double in speed, or not double in speed, but double in frequency. Basically, how many times you'll have it per second. The blue sine wave that I drew happens once in this amount of time, whatever that might be, while the beat happens twice. So again, from a mathematical perspective, this omega n minus omega represents this overall sine wave here. But when we think about the physical consequences, the thing that we really care about is the beat. When does the beat start over? So it ends up being half. So by definition, omega beat is the numerator of this guy because we're taking away the half. We're essentially doubling the frequency, the mathematical frequency we see from the sine wave. That'll cancel out the twos, and then you're left with omega beat being the difference in the natural frequency and the driving frequency. And you'll see that a lot of times in the book, they'll do absolute values because, again, the sine will just impact the phase of it. But in general, if we want to know how many beats we have, in this case, it's in radians per second, how many beats there are in an angular frequency perspective would be the difference between the two frequencies, the natural frequency and the driving frequency. So these two things are happening simultaneously. Now, once you figure out what those two are, again, it can be a mathematical thing where they give you in the problem, like your homework problem that I did in the recitation, where they give you the periods of the beats and you can go ahead and convert them to frequencies and you have a system of equations. Or you can look at a graph and then figure out how many oscillations do I have in a second, or what is the period of the oscillations? When does the beat start again? That type of thing. Really, this omega beat, if this is not like the best way of writing it, it should be T beat, because if I'm looking at the x-axis, that extent is in time. But I'm just trying to show you that that is considered one cycle. Yeah, omega beat is not really, that is considered one cycle, that whole thing, that beat. So depending on the amount of time it takes for that to happen, you can figure out how many cycles you get per second. So hopefully this makes sense. If it doesn't, please let me know, and I can go ahead and answer questions directly or make another video or something. Okay, thanks. Bye.